Hi everyone, my name is Celso de Oliveira, and today on behalf of Santos Dacal and Dr. Ramesh Malla, I present the field testing and finite element modeling of selected truss railroad bridges in Connecticut. Presentation overview. In this presentation, I'll start by introducing the project importance and objective. Understand the theory behind the dynamics and data processing. In section 4, I'll introduce the Devon bridge. From section 5 to 9, I'll present the youth sensor, testing, and simulation methodology, results, and conclusion. And to wrap up with acknowledgements and reference. Background and importance. As we all know that passengers and freight trains are vital to maintain a thriving economy, especially in Northeast Corridor. Preserving a reliable railroad system is expensive and requires constant infrastructure upgrade, improvement, and eventual replacement. Since the majority of New England railroad bridges are old, research is needed to extend the life cycle of those bridges. Project overview. The primary objective of this project is to develop an efficient, cost-effective methodology for short and long-term structural response, health monitor, and assessment of both new and existing railroad bridge using analytical, computational, and experimental techniques. Dynamic theory. First, we start with the equation of motion. Since our system is assumed to be undamped, the damping component is neglected. The equation 2 represents the free vibration of the system, and by combining 1 and 2, we have the free model analysis that is shown in 3. Most of the time in small systems, the internal stress is neglected. Since we are dealing with a large mass, it's prudent to include the stress created by permanent load, in this case the gravity. The equation 4 represents the pre-stress model analysis, where the S is the stress stiffness matrix derived from the permanent or moving load analysis, in this case static or transient analysis. Data processing theory. The filter represents the replica of harmonic vibration with a sinusoidal shape and is shown in the equation 5. For mathematical analysis and data processing, it's advantageous to use a complex number to describe the harmonic vibration. The harmonic vibration ut can be written in equation 6. Any recorded time signal can be transformed in the frequency spectrum using the Fourier transformation, in which a convergent infinite series of trigonometric functions are described as periodic function, as shown on equation 7. By combining 1 and 7, we have the transformed equation of motion, represented in the complex number domain in equation 8. The function in Fourier domain of transfer function is represented in equation 9, where the input represents the excitation, in this case the reference from the shaker, and the output represents the sensor reading, individual sensor reading from, it can be from accelerometers or the vibrometer. Devon Bridge overview. The bridge is located over the lower Housatonic River between Milford and Stratford, Connecticut, and it was built in 1906. Devon Bridge has 7 spans. It's a combination between deck girders, wooden truss, and Chiser rolling lift bascule. 2 field tests has been performed on the bridge, and few more are scheduled to be performed during the summer. Field test sensors and devices. For the field test, we use 3 different type of devices. We use accelerometers, laser vibrometer, and the bridge shaker. In the accelerometers, we use 2 different type of accelerometers. We use the quad sensing elements, which we describe as a conventional. We use the micro electromagnetic sensors, which we describe as a standalone. They don't require data acquisition system. They don't require wiring. And we use a laser vibrometer. We use a 3D compact scanning vibrometer from Polytech, PSV 500, and we use a bridge shaker as well, APS 113 electrostasis. Test 1, October 28, 2020. For this particular test, we use 3 laser vibrometers, 3D laser vibrometers. We use 3 conventional accelerometers and 1 shaker. All the test was made on the span 7, shown on figure 4, and even the final element model was to mimic that particular span. And Figure 5 shown the test setup where we place 3 vibrometers and 2 on each side, which is vibrometer 1 and 3, and 1 in higher ground. We use a lift in order to place the vibrometer so they could triangulate the point and have the three direction, X, Y, and Z response from each point. And then we place three accelerometers on the bridge, as you can see as well in the figure, shown in the figure. And the shaker as well was placed in one of the vertical posts. Test 1 results. After processing the data using the theory describing above, the figure 6 shown the velocity frequency from the free vibration, where we clearly can identify the three nitro frequencies, the peaks. And in figure 7, we have the velocity frequency from the shaker at 4.8. And on table 2 is the comparison from different analysis, and the natural frequency identify the three mode shapes. Figure 8 shown as the mode shape of the vibration using the root mean squared from the harmonic vibration at 1.3 hertz. Test 2, January 23, 2021. From this particular test, we use 5 standalone accelerometers, and figure 10 showed the sensor location. And before we use the standalone accelerometer, we calibrate the standalone accelerometer. We make sure that the results are acceptable. And we place them on the vertical post, between the vertical post and the floor beam, as shown in figure 11. And the good thing of these accelerometers, there's no data acquisition system, there's no wire, and the big disadvantage, it's hard to do the synchronization. So we need to read each accelerometer individual. As you can see in the figure 12, that's a reading from accelerometer 3 from one train passing over the bridge. Right now, we're still processing this data. And finite element model, Devon bridge. For the finite element model, we use the ANSYS 2020 R1, and we perform 3 different analyses: unload model analysis, static structure analysis with a permanent load, and pre-stress model analysis with a permanent load. We encounter a few challenges, such as using the drawings from 1905, the build-up member using rivet connections, and detailing I-bars, and using vintage steel, which is the A7 steel. Final element model, geometry. That was the first challenge that we encountered to model the build-up members and with the rivet connections. Since most of the members are composed with angles and plates. So the first thing we did was to dig on the drawings. For example, as you can see, that's a vertical post on figure 14. That's the model process. The 4 figures from the left to the right showed the modeling process. We have the plates and angles, then there are some cross bracing. So the first thing we dig onto the drawings, we extract the cross sections, we model using the right cross sections, the angles, the plates, all those things, and eventually we combine everything and we replace the cross bracing by a thin plate. I believe was 1/16 of an inch, and from there we extrude. So that slightly changed the cross sections, the cross section property, but we try to minimize that change using that process. Finite element model material. The original steel material from the bridge is A7, and it was discontinued in the late 1940s. We use a limited number of specimens shown in figure 15, and we use tensile tests to extract the tensile strength, extract the Young modulus, and from there we compare with the default steel material. And shown on table 4, we have the comparison between both of them, and we found that the difference is less than 5%. So therefore, for that particular analysis, we use the default steel from the ANSYS. Finite element model setup. The idea of the model was to mimicate the span 7 of the Devon bridge. Since the Devon bridge is a simple supported spans, so we'll try to mimicate that behavior. So we left free in the X direction in one of the supports, and we fix on the X and Y and Z direction. So figure 16 showed the model analysis without any preload or self-weight or permanent fixtures. Well, in the figure 17, we have the static structure analysis, where we include the self-weight of the structure and we include the permanent fixtures such as tracks and cross ties. Finite element model, static results. On figure 18, we have the undeformed model. On figure 19, we have the deformed model due to the self-weight of the structure and the permanent fixture. The self-weight was calculated automatically by the software since we input the closest cross-section and the software knows the density of the material. It can automatically calculate the self-weight. And the permanent loads we add manually, which includes the 200 pounds per linear foot of track, including tracks and fastener per ARIMA, chapter 15, section 1.32b, and 243.42 pounds per linear track to account for the wood tie per Connecticut DOT report. Finite element model analysis results. On figure 20, we have the unload model analysis. In figure 21, we have the pre-stress model analysis. And from those figures, we identify the three global natural frequencies and the respective mode shapes. From the left side, by comparing the figure 20 and 21, in this case the unload model and the pre-stress model, we can see there is a shift between the natural frequency. We change, for example, in the mode shape 1 from 1.5 to 1.8 almost. So that's almost the same behavior as a guitar string. The more tension we give to the guitar string, the natural frequency is going to change. The sound wave is changing as well. So that's the same principle, and the same principle we can see on the mode shape. You can see on the left side, you can see well-defined mode shapes, and on the right side, there is less deflection due to the pre-stress. Results discussions. The results from the field tests and the finite element model is close to calibration. The pre-stress finite element model and the harmonic vibration from the field test show a difference of less than 5% as shown on table 5. Conclusion and application. The pre-stress finite element model has shown better results in comparison with the field test. Additional pre-stress model from service load, such as a moving train and field test, will be used to validate the model, and it's scheduled to be performed during this summer. Sufficient sample from the regional material of the bridge will be used to support the material selection properties. With the updated model, different simulations of different scenarios, such as a braking, traction, wind, and other, will be used to identify and to analyze the critical members and connection. Same concept will be used to update other selected bridges, such as the Costco Bridge on figure 22. And we are hoping that with this, what we learned from Devon Bridge, we can reduce the fraction of time to calibrate the future bridges. Acknowledgements. The research team extends its sincere thanks and appreciation to Transportation Infrastructure Durability Center at the University of Maine, the 2018 Region 1 US DOT UTC for partial funding this project. Connecticut Department of Transportation for continued support and feedback. Metro North for the continued support and providing the material. Polytech for providing the part of the equipment. For the University of Rhode Island, for LONAS, the standalone accelerometer, special to Dr. Braxton and Dr. Lee. For the University of Connecticut, for partial fund this project and for the lab facilities. To all the students involved in the project, graduate or undergraduate. References. Thank you. Questions?